Lesson 11-5, Growth and Decay. And in this lesson, you learn to solve problems involving growth and decay. Why is it important? Because you can solve growth and decay problems to learn more about demographics and energy. Let's take a look at this real-world application on demographics. How quickly has the population of your state grown in the 20th century? So both California and Nebraska have grown in population by a constant percent. The graph shows the population in each state, where T represents the number of years since 1900. Since 1900, the population in Nebraska has grown at the rate of 0.4% per year, while the population in California has grown at the rate of 3% per year. Okay? So the exponential functions that model the growth of each state are given below. So in California, this is our exponential function, 1.77 times 1.03 raised to the t power. The population in 1900 was 1.77 million. Okay? And uh, 1.03 represents the 3% per year. Okay, and Nebraska is 1.14 because the population 1900 was 1.14 million raised to the 1.004, and this represents the uh, uh, growth per year in Nebraska. 0.04% is the same as 0.004. Okay, so question is, which state exhibits more rapid growth? What will the population of each state be in the year 2000? And your answer, you will answer these questions in exercise 1, and if you just look at the graph, you more or less have an answer to the question, which state exhibits more rapid growth? Okay, so let's not jump the gun here, and let's take a look at uh, the equation for the two states. Okay, so the equation for the two states populations are variations for the equation y equals c times the quantity 1 plus r raised to the t power, and this is the general equation for exponential growth. And I want you to write this down. This is the first formula you are going to memorize in this section. So you have y equals c times quantity 1 plus r. Okay, the general equation for exponential growth, in which the initial amount c increases by the same percent r over a given period of time t. So this equation can be applied to many kinds of growth applications. And one of these growth applications that we can use is monetary growth. Okay, so money. When solving problems involving compound interest, the growth uh, equation becomes A equals, okay, and we applying now our uh, general equation for exponential growth. We can vary it a little bit so it will fit our needs for money, and this is the equation that we will use when you're talking about monetary growth. A equals P times the quantity 1 plus R over N raised to the NT. Okay, a little variation of our general equation, but this time this is for monetary growth. So in this case, A is the actual amount of investment over a period of time. P is the principal, initial amount of investment. Okay, uh, R is the annual rate of interest, and remember, annual means yearly rate of interest expressed as a decimal. N is the number of times that the interest is compounded each year, and T is the number of years that the money is invested. Okay, so how do we use this? Using how would you use that formula? Let's take a look at example 1. So in the spring of 2000, Mr. and Mrs. Mitsu had $10,000 they wished to place in a bank certificate of deposit, or CD, towards their retirement in the year 2010. So So the interest rate at this time was 2.5% compounded monthly. However, there were 7 increases in the prime rate in the year, so that in the spring of 2001, the interest rate had risen to 5.5%. Okay, so let's talk a little bit about this problem. So when you talk about money, okay, when you graduate and you find a job, you'll notice that investment is one of the things that you will be doing with your money, investing it in a company or investing it in the stock market. Okay, and there's such a thing called the prime rate. The prime rate is basically the interest rate given to investors who have great credit. That means they have a great track record, and that's the reason why they're given the prime rate. Okay, so let's reread the problem. The interest rate at that time is 2.5% compounded monthly. That means you compound this every month. Okay. However, there were 7 increases in the prime rate in the year, so that in the spring of 2001, the interest rate had risen to 5.5%. So the prime rate increased, and the interest rate had gone up to 5.5%, which is a good thing. Okay, as the interest rate goes up, okay, uh, your investment actually grows, okay, a lot faster than if it were 2.5%. So the question we are asking is determine the amount of their investment after 10 years if they invested the principal and let it remain at 2.5 interest rate. Okay. And letter B, determine amount of investment after 9 years, okay, if they waited and invested the principal at the 5.5, okay, percent rate. So what are the best options for their investment? So we want to find out the best options that Mr. and Mrs. Mitsu will have for their $10,000. Letter A, okay, let's start with letter A. We want to determine the amount of their investment after 10 years if they invested the principal and let it remain at 2.5 interest rate. So the interest rate R as a decimal is 0.025 and n is equal to 12. Why is n equal to 12? Remember, compounded monthly. So that means, okay, since we're talking about 1 year, okay, there will be 12 times it has been compounded. That's why it's 12. We use the formula A equals P times the quantity 1 plus R over n raised to the nt. And then we simply substitute the value for P, which is 10,000, and for R, which is 0.025, the decimal of our rate, okay? And N will be 12, and T will be 10 for 10 years. So this is how it's going to look like. 10,000 times the quantity 1 plus 0.025, which is the rate, all over 12 compounded monthly for a year, okay, multiplied by 10, which is 10 years. Okay, and we use a calculator to do this. Okay, using a calculator, we simply enter 1000 times parentheses 1 plus another parentheses 0.025 divided by 12 parentheses parentheses close parentheses 2 close parentheses, then click on y to the x. Okay, 120, because 12 times 10 is 120, equals 12,836.91542. So the amount of the account after 10 years at 2.5% is 12,836.92. Okay, so let's take a look at letter B. Letter B, it's asking determine the amount of investment after 9 years if they waited and invested the principal at the 5.5 rate. Okay, so let's take a look at letter B. If they waited the interest rate at 0.055 and t is equal to 9 years. So again, we use the formula. Okay, and when we substitute the values to the formula, we now have, instead of 0.025, we now have 0.055 because it's 5.5 interest rate. okay, compounded monthly for a year, which is 12, but instead of 10 now, we simply multiply it by 9. And we end up with 16,000, approximately $386.44. So, letter B, if they waited, okay, will give a better yield to their investment compared to letter A. But it's asking what are the options that the Mitsus can take. This is what we can advise them. If they waited until the rate went up, they would have had more money than leaving the money at the initial rate. We know that. However, if it is possible to reinvest the money each year, they could have invested the money for 1 year at 2.5%, so they don't lose that year, and then reinvested the next year at 5.5%. That would yield even more money for their retirement in 2010. Okay? And this is what your parents go through when they invest their money in the stock market, okay, to see which is the better deal. Okay? And let's take a look at the next concept in this lesson. We talk about exponential decay. We talked about growth. Now let's talk about exponential decay. So the variation of growth equation can be used as a general equation for exponential decay. And this is the formula for exponential decay. Memorize this. A equals C times the quantity 1 minus R raised to the T. Again, instead of a plus, okay, this is a minus sign, which indicates exponential decay. So A represents the final amount, C is the initial amount, R is the rate of decay, and T denotes time. Okay, so let's take a look at example 2 and see how this works. The cities listed at the right have experienced declining population since 1970. In Baltimore, Maryland, you have 1970 population at 894,000. Annual rate of decrease is 1.029%. And in Cleveland, yeah, 1970 population 733,000, and annual rate of decrease is 1.055%. So people are leaving both states or both cities. Okay, so if T represents the number of years since 1970 and C represents the 1970 population, write an exponential decay equation for each city. So we will do that. Assume that each city maintains the same decrease rate into the next century. Calculate the population of the city in the year 2070. So that's 100 years from 1970. So how do the projected populations of the cities in 2070 compare to the actual population in 1970? So we'll answer A, B, and C respectively. Let's start with A. Okay? Write an exponential decay equation for each city. In Baltimore, okay, your C is equal to 894. Your R is your rate of decay, which is 0.01029, decimal of 1.029%. Okay, so our formula for exponential decay is C times the quantity 1 minus R raised to the T power, and then we simply substitute that. We have our, okay, we have our expression now, and if we subtract 0.0102921, we'll end up with our expression 894 times 0.98971 raised to the T power. And we'll do the same thing with Cleveland. Again, our C is 733, R is 0.01055, the decimal of the rate of decay. Okay, so the annual rate of decrease of the population, that's the decimal of it. And then we use the formula for exponential decay, substitute the values, simplify that, and we have 733.98945 raised to the T power. We've answered letter A. Okay, we wrote exponential decay equation for each city. And letter B, assume that each city maintains the same decrease rate into the next century. Calculate the population of the city in the year 2070. So the year 2070 is 100 years later. So evaluate each decay equation for T equals 100. And then we use the expression that we used in we found in letter A. and then we substitute the value of 100 to t, and then using a calculator, A is equal to 317.78. We'll do the same thing with Cleveland. Get our expression from A, substitute t with 100, end up with A equals 253.8. Okay? And finally, letter C, how did the projected populations in the cities of 2070 compare to the actual population in 1970? In 1970, the difference in the populations in Baltimore and Cleveland was 161,000. In 2070, the difference is only about 64,000. Okay? So if the populations would continue to decrease at the same rates, they would grow even closer to each other. Okay? And that's how you answer letter C. Okay? And the secret word for this particular lesson would be macadamia. Secret word is macadamia. Okay, and let's take a look at the next one. Sometimes items decrease in value. For example, an equipment gets older, it depreciates. You can use the decay formula to determine the value of an item at a given time. Okay, and a good example for this one is a car. A car, once it leaves the lot of, let's say, the car dealership, the car begins to depreciate right away. And that's the reason why, for example, generally speaking, a car is not a good investment because the value of the car depreciates as you drive it every day. So let's take a look at example number 3. Hogan Blackburn is considering the purchase of a new car. He is faced with the decision to lease or to buy. So if he leases the car, he pays $369 a month for 2 years, and then he has the option to buy the car for $13,642. So the price of the car now is $16,893. So let me just explain to you the difference between lease and buy. When you lease a car, you basically pay a monthly amount, but you don't get to own the car unless it is buy to own after the lease period is over. You're basically renting the car for a period that you wrote in the contract. A more common time period would be 3 years. Then after that, you return the car to the dealership, and you either lease the car or you lease another car, or you decide to buy the car that you just leased. Okay, buying a car is straightforward. You simply pay monthly for the car, and you own the car after a period of years, depending of how many years you chose to pay for the car. Can be 3, 6, can be 3, 5, or 6 years. Okay, to purchase the car. So letter A, let's see the situation that he is faced with. If the car depreciates at 17% per year, how will the depreciated price compare with the buyout price of the lease? When you say buyout price of the lease, after the lease period is over, you can buy the car for the price that that is remaining on the car after the lease is over. Letter B, at the end of the lease, the dealer offers a loan for 3 years at the rate of $435.79 per month. Okay, so if Mr. Blackburn buys the car now, he will pay $464.56 monthly for 4 years, which is the best way to go if he plans to keep the car for at least 5 years. So we will help Mr. Blackburn decide whether to lease or buy the car. And obviously, since we're talking about depreciation, we use the decay formula in letter A, which is A equals C times the quantity 1 minus R raised to the T power. And C in this case is 16,893. Okay, the price of the car now, initial price of the car, and then the rate is 17% per year. So you have 0.17. Okay, and we simplify that. You have now 11,637.59 using a calculator. Okay, so the depreciated value is 2,000 less than the buyout price. Remember, the buyout price is where's my buyout price? Okay, here you go. This is your buyout price, 13,642. Okay, and the depreciated value is 11,637.59. What does that mean? It simply means this, that after 2 years, the value of the car is 11,637.59. Okay, but if you want to buy the car, it will still be at 13,642. So you can see this is the value of the car after 2 years, but this is the price they are still asking from you to buy the car. Okay, so that's the reason why it says the depreciated value is 2,000 less than the buyout price. So letter B, at the end of the lease, the dealer offers a loan for 3 years at $435.79 per month. If Mr. Blackburn buys a car now, he will pay $464.56 monthly for 4 years, which is the best way to go if he wants to keep it for at least 5 years. So we need to calculate for the cost of each possibility over a 5-year period, and we look at lease and buy. So lease and buy means $369 a month for 24 months, 2-year lease, and then you have $435.75, which is being offered to Mr. Blackburn for 36 months to buy the car. At the end of the lease and buy period, Mr. Blackburn would have paid $24,544.44. But if Mr. Blackburn buys the car outright, he will pay $464.56 for 48 months, and he would only have paid $22,298.88. Okay, it seems right here it's pretty clear that you need to buy instead of lease and buy. But again, it depends on Mr. Hogan's financial status. Okay, so the overall the buy option costs less and lasts only 4 years, while the lease and buy option costs more and lasts for 5 years. Okay, now that is the best way to go. Okay, if he's good with money, if he doesn't have to worry about money when he starts buying the car, because the monthly will be a lot bigger. But on the other hand, if Mr. Blackburn really wants a new car and cannot afford the larger monthly payment now, okay, so he would pay the lease option, maybe best, because he only pays $369 for 24 months. However, he will eventually have to make the larger payment if he keeps the car. So if Mr. Blackburn does not have the money now, the lease and buy option would probably work. But if he has the money, then the buy option always is the best option. Okay? And that is the end of our lesson. Thank you for watching.